Thank you for coming to my talk, and thank you, Christopher, for nice introduction. So today I'm talking about some machine learning project in BIFOLD for quantum computing. And here we recently defined a notion called confidence region, and we proposed a few approaches for quantum computing. And this work is done in collaboration with many people, including Christopher, now in AIP, but previously in our group. Okay, so I first talk about what is confidence region, and then after this, I introduce a specific quantum computing protocol called variational quantum eigensolver. And I talk about our recent proposal for solving this problem. Okay, confidence region. So intuitively, confidence region is the input region where machine learning model can confidently predict. So if I explain this with a figure. So let's say we have two observations of the input-output relation. And then if we apply some machine learning model, like Gaussian processes, then the model can predict like this. So here, the blue curve is the mean prediction, and the green curves with range corresponds to the uncertainty. And then we simply define some required accuracy kappa, and then confidence region is the input region where uncertainty is small enough. So we set kappa, and then this is the threshold to be confidence region. Okay, and as expected, so if we have one more observation, for example, like this, then the confidence region expands. Okay, and so we propose this notion and use this for Bayesian optimization and some related method. So probably almost all know about Bayesian optimization. So the goal is to minimize some unknown function f star, and typically we can rope this function by observation, but the observation is costly, and then the goal is to minimize this function with minimum observation cost. And typically we define acquisition function which somehow express the promisingness of the observed point x prime, and somehow Bayesian optimization is formulated as a maximization problem, and we just design acquisition function. And there are many acquisition functions, and probably most common is expected improvement, where in this equation, so the first term, the blue part, is the current best function value, and the second term, the magenta term, is the predicted term, and then with the hinge rows, we focus on only the improvement, and then we take the expectation, and then acquisition function somehow expressed the expectation value of the improvement with respect to the current knowledge of the machine learning model. And there are some variations, like noisy expected improvement, which considers the noise of the previous observations. And also there are variants which consider multiple new inputs. And so there are several this kind of acquisition function. But one problem of previous method is actually those acquisition function doesn't really care about the uncertainty at the new observed point. So meaning that, so this function says x prime, the point x prime is promising, but it doesn't really consider how much effort we need to find the function value at x prime. And with our confident region, we can do this.
I ask a question.
Yes.
What's the difference between the EI and the EI? I didn't see
Difference between what?
The two criteria.
Okay. So this one
Yeah.
is, so this y1 to yn are just the previous observation endpoints. So they are just observed value.
So what is f of x1? It's not y1?
F of, sorry?
Because in the definition of noise expected improvement, you replace y1 with f of x1.
Okay. So F is the machine learning model. Okay, so I didn't say this. So F star is the unknown function which we want to minimize. And F is its approximation, its surrogate function to approximate F star.
But I think I thought you are doing Bayesian, but then this is frequentist, right? Because
No, so this is, I mean, this is the posterior distribution.
Okay, I see.
So
I see.
I don't really know the very difference between frequentist and Bayesian, but at least we use base posterior. I mean, from Gaussian process, for example, and then the difference is these are just a noisy observation, and this expected improvement simply use the just trust the previous observation. But here we observed this point, but still we are not sure about the function value, and then we take the expectation value over the previous observation as well.
Yeah, because MT also said that the data is fixed.
Okay.
The data is fixed. So I really argue with him if we sample the 2 point again, whether we will get the same data.
So you mean so here we fix the data, right?
Yeah.
And then here we fix the data here. But
no, it's not fixed. Because here there's no data. At least there is no output, right? Because
it's not, so X is input, training input, and Y is training output. So Y is observation.
but there is no Y in the equation.
In which equation?
In the second equation there is no Y, right?
Oh, this is Y.
Oh, okay. So you mean the function f depends on x and y?
Sorry, Y is not a function. Y is just the observation.
No, the function f.
Function
F is
f?
the model. F depends on x and y. That's the only dependence of this equation on y.
Yes. So I mean in this way. So in this
Yeah,
region.
okay. Okay.
Okay. So thank you for your question. And probably I didn't explain this. So okay. So this is our proposal, one of our proposal called expected maximum improvement over core. So it's EMICO we pronounce. And basically the roughly it has the same form as expected improvement, but the first term is the best value over the prior confident region. And the second term is the best value over the posterior confident region. And here I said core, prior core and posterior core. So prior core is the core with the current knowledge before new observation, and the posterior core is the expected core after new observation. So then we simply take the minimum value within the prior core because we are already sure about the function value in the prior core in the previous step. And then for the next step, to find the best new observation, we investigate the posterior core and take the minimum over the new core region. So basically, the second term, the minimizer of x for y for x is not necessarily one of the new observations, but basically any function value of any places within the posterior core. Okay, and probably for now, you would wonder if this is really considering this core beneficial, and so I will explain under what situation core is very beneficial. So one situation which actually happens in quantum computing is that the core extends beyond neighborhood of the observed point. So what this means is, so this is very typical view of Gaussian processes. So if we measure a single point, and then the machine learning model is confident only in the neighborhood. And if we observe other 2 points, then we just have posterior core, which corresponds to the neighborhood of the observed point. But in some cases, something like this happens. So we just measure 2 additional points, then actually the whole 1D space is within the core. And this actually depends on the setting of the kernel function. And this, I will explain the detail from now on. Okay, but before this, so okay, so I should tell this thing. So if this happens, meaning that with only a few points, we have a huge expansion of posterior core, then we don't need to observe the most promising point, because most promising point is not necessarily the minimizer of the predicted function. And actually, what typically happens is we should observe some point with good span, so that the whole 1D space is within the core. And then we could say this is the minimizer because it's within the core. So this flexibility we can use by defining the notion of core. Okay, so this is the most promising situation where core is beneficial. And another situation is when we can control the observation accuracy. And this actually happens in quantum computing as well, because quantum computing is quite noisy. And usually when we measure some point, we use hundreds or 1,000 measurement shot. And if we reduce it, we can reduce the quantum computing cost. And by using this property, we also proposed other method, which I will explain. And the last situation, which I won't talk about, but one master student in our lab worked on this amico applied to some other application other than quantum computing, and where the epistemic uncertainty and aleatoric uncertainty are separately given. And actually, when epistemic uncertainty and aleatoric uncertainties are known, when we compute amico, they contribute differently. And then we can somehow optimize our strategy by using the uncertainties. And this master student showed some benefit, but today I don't talk about it. Okay, so that was the introduction, and now I will talk about, I will briefly introduce variational quantum eigensolver, which is a hybrid, the classical quantum computing protocol to find the ground state energy for a given Hamiltonian. So basically, physicists set some Hamiltonian, and they want to know the ground state energy. And this is F star, the objective function, which we don't know. And actually, we can compute the, we can observe the energy. So ground state energy is the expectation value of the Hamiltonian. And by using quantum computer, we can observe this value. And how we do this, so we have a quantum circuit, and it starts from some quantum state P0. And then we prepare some quantum circuit, which makes some rotation operator or some correlation between qubits. And then this rotation gate has some parameters. And somehow we can modify the initial wave function to the output wave function. And then the parameters are the angular, so this is the polar space. And then in variational quantum eigensolver, we solve this minimization problem, so which I wrote classical computing. And the objective function is in this form. So basically, this part, so Px is can move in some wave function space, and if the quantum circuit is flexible enough, it can approximate the ground state well. And in that case, if we minimize the energy, then we can get the ground state energy accurately. So this is the variational quantum eigensolver, and our goal is to efficiently minimize F star. And so again, so this is quantum computer, and actually it's noisy because quantum mechanics, we can only observe some with some randomness. So it's inherently noisy, and we need to minimize this objective function from noisy observations. And there are several state-of-the-art methods which physicists use. So one is called Nakajima Fuji Todo, which is, I mean, apparently proposers Japanese, and they proposed a kind of sequential minimal optimization method, which I will explain detail. And another approach is just the stochastic gradient descent, but because the objective is noisy, they also use some specific trick specialized for PQE, which I will explain also a little bit. And also some people tried just standard Bayesian optimization. And so our group tried this problem by mixing up these three methods, basically. And all the methods, the key notion is the core, which I explained. Okay, so actually, there is good news, and so actually there are good properties of this problem. So the quantum circuit is a sequence of gates, and some gate has parameters, and some other gates doesn't have parameter. And an important point is that each parametric gate is a unitary of rotation operator. So these are Pauli operator corresponding to the rotation along x-axis, y-axis, z-axis. And by using this constraint, one can show that the objective function has this function form. So it's a tensor product, and it's very looks a little bit complicated, but basically the function lies in a finite dimensional space with a low order Fourier series. So basically for each along each axis, it's just a sine function or low order Fourier series. And I explained the simplest case with the first order Fourier series. And in this case, what happened is that, so let's say we are at some point in the optimization space in X, and we only choose the one direction, and we moved. And with other entries fixed. And then what happened is that the function dependence on a single variable is just a sine function. So this means that it only has degrees of freedom 3. So then if we observe just 3 points, we can estimate the complete function form along this direction. So then what we could do is, let's say we have information on 3 points, and then we just fit the sine function and take the minimum. So this way, one day of the optimization can be done with just a few of the observed points. And then by using this property, the Nakanishi Fuji Todo applied sequential minimal optimization. And SMO is, the goal of SMO is just a minimization of unknown function, and basically just minimize a small dimensional subspace iteratively. And this method, NFT, performs SMO with only 2 observations at each step. So let's say this point is the current optimum, and then we just choose a direction to optimize, and we observe 2 points, and then with these 3 points, we can estimate the function form and analytically obtain the new optimum, and we just iterate to the next direction and like this. So this method is actually an efficient state-of-the-art method which physicists use. But one problem is that this method doesn't consider the observation noise. And then we applied a machine learning method to take the noise into account. And actually, we used Emiko, which I explained in the beginning, and tried two things. So one thing is, by using Emiko, we can compute the acquisition function for directions. So let's say we are at some point, and then we could choose a new direction by computing Emiko. And then another possibility is that we don't change the choice of the direction, but we somehow optimize the new two points. So here typically physicists use pi/2, but this is not really optimal. So we can choose this by using Emiko. And actually, we tried both, but the choosing the direction was not so successful, so we didn't see a gain. But choosing two new observed points, we got some good results. Okay, so but before applying Emiko, I will explain a Bayesian version of NFT. So this is simply the NFT method with some machine learning. And here we use Gaussian process. So when we fit the sign function, we can just use the Gaussian processes. And one good thing is, so NFT method always use just 3 points, the previous best point and new observation. But we can use much more previous observations. And this is beneficial, especially in the converging phase, where the optimal point doesn't move a lot. So then previous observations are close to the current observed point. So we can somehow accumulate the information and make the prediction more accurate. And here we need to use a special kernel. So if we simply use, for example, Gaussian kernel, then we cannot use the property of the variational quantum eigensolver, where the function, objective function, is just a low order Fourier series in each direction. But if we use this kernel, which we call VQE kernel, but it's a generalization of Dirichlet kernel. And this kernel we can decompose into the feature vector or basis functions, and then this basis function exactly match the basis function of the VQE. Okay, and then this simply compares NFT versus Bayesian NFT. And here I don't explain much, but basically lower is better. And then solid curve is the Bayesian version, and dashed curve original NFT. So applying GP with VQE kernel already gives some benefit. Okay, and then we use Emiko for this problem. And as I explained before, so basically if we use the VQE kernel, this happens. So just 2 more observations expand the posterior core significantly. And then this application fits this Emiko very well. And then we just optimize these new points by maximizing the acquisition function Emiko. And then I introduce some experimental results. So we use some typical quantum circuit, which is called L-layered efficient SU2 with some qubit value and the number of layers. And then we set some benchmark Hamiltonian, Ising Hamiltonian and Heisenberg Hamiltonian. And we actually didn't really use quantum computer, but just rely on classical simulation. And these are the results. So left-hand side, this is the achieved energy. So this is the minimization of the objective function. And red corresponds to MCO, and the other colors corresponds to the baseline. And the right-hand side, we also plot the fidelity, which is the inner product between the quantum circuit output and the ground state energy. So for this small cases, we can compute the wave function analytically, and we can check these quantities. And for small qubit, the difference is not that much, but if we go to larger setting, the difference is significant. Okay, this was MCO, and I will shortly introduce the other two called subscore and GradCore. And subscore is the method for adaptive control of quantum computing cost. And as I said, quantum computing cost corresponds to the measurement shot of the quantum computing. And what subscore does is like this. So first, we need to specify the required prediction accuracy, kappa P, and this need to be designed well so that at each phase of the optimization, the required accuracy is reasonable. And then, so if we can set it, then subscore minimizes the quantum computing cost under the constraint that each subspace, so 1D subspace of NFT is within the core. So this figure somehow illustrates the situation. So this is the prior core. For the new direction, we always sure about the current point, and then we need to measure some other points with different amount of measurement shot, and we control this so that the whole 1D space is within the core, but don't use too many number of measurement shots. And with this, we get some improvements. And so this is the last one, which is called GradCore. So we did some similar approach for gradient descent optimization. And here, again, physicists use some trick for specialized for VQE, which is called parameter shift rule. So this is parameter shift rule is a method to estimate the gradient. And if you see this equation, so basically it's quite similar to finite difference. So to compute the derivative with respect to the direction d, we measure the function value slightly to the left and slightly to the right, and then take the difference. But an important difference is that we can take alpha, that span, to arbitrary value. So it's not a finite difference. So if we do finite difference, alpha must be small enough. But we can set alpha arbitrarily, and this is because of the property of VQE, where the function is just a low order Fourier series. And then what we did is we first make it Bayesian. Just mean that we use GP for gradient prediction. Actually, gradient prediction of GP is straightforward because gradient is just a linear operator. And then we define core for the gradient estimation. And so basically, grad core, our method minimizes this quantum computing cost such that the current point is within the core. And we just optimize the necessary quantum computing cost to get reasonably good gradient estimator. And we applied, we compare again and always replace the new method. And this method outperforms all the previous method. Okay, so these are our recent work. And I just briefly mentioned about future plan. So we propose EMI-core, top-score, and grad core, and they are, we somehow propose separately, but it's clear that they can be combined. So we can do Bayesian optimization, including the cost adaptation. And also this EMI-core and sum-score is the NFT or SMO-based method, and grad core is SGD-based method. And we found that SMO-based method is very good in the beginning of the optimization, but in the converging phase, it's not very stable, and we found gradient approach is better. So we need to somehow combine this method to get optimum strategy. And another future work is, as I mentioned briefly, about our master student project, where electric uncertainty and epistemic uncertainties are separately considered. And if we think about EMI-core acquisition function, for example, the magenta part, which corresponds to the observation cost, this should be related to the electric uncertainty, and then the other part is related to epistemic uncertainty, and we somehow develop a system where we can efficiently or effectively use these two different uncertainties. That's it. Thank you for your attention.
Thank you very much, Shin, for the amazing talk. I think you may have a lot of questions, so please raise your hand or ask if you have any. Okay.
Yeah, thank you very much for the interesting talk. I try to follow every point, but for me it's still very difficult. Yeah, I have two questions. The first question is the definition of noise in your presentation. I want to confirm that you mean the noise means the uncertainty due to the superposition, rather than the lack of information about the quantum states, right? So it means that you assume that we are dealing with the pure states. We know the full information of the quantum states is a closed system.
No, you mean so okay, so we don't consider hardware noise. Do you mean this?
Yes, the hardware.
Okay, so here we don't consider hardware noise.
Okay.
It's just
see.
statistics from
I
the
see.
quantum
I
mechanics.
see. Yes, very much. And my second question is about the VQE kernel you defined in your slides. Could you go back to that slide? Yeah, thank you very much. Yeah. So thank you. So what I see this formulation, if we take the logarithm on both sides of the equation, so on the right hand side is equivalent to a kind of Fourier expansion of some function. I'm not sure my memory is correct or not. The right hand side can be converted to some Gaussian function.
Sorry, left hand. Oh,
The right hand side.
right hand side.
Yes, if we can consider the dimension d extend to the infinity, the function on the right hand side goes tend to the Gaussian function. I'm not sure it's correct or not.
Sorry,
So
I don't know. Okay, but you know that.
I'm not sure if my understanding is correct. So I have a question that if the right hand side is close to tend to the Gaussian noise, the Gaussian kernel, so why there exists the differences shown in the next slides? The next slide you show the differences.
The whole kernel or the whole figure function can be accompanied by a single Gaussian function.
Yes, if we consider if the dimension d extends to the infinity, I'm not sure. This is just my general comment.
Guys, so converts to Gaussian maybe somehow in the sense of central limits theorem, like take log and
Take log and right hand side is a kind of Fourier series, right? It's the summation of cosine function and the sine function.
okay, log of time function.
Yeah. It's a log of sine. Sorry.
So this is product.
Yeah. Oh, okay. Maybe I made some mistake.
Okay.
Yeah. Sorry. Yeah. Okay. I have no questions. Yes. Thank you very much.
Any more questions?
May I ask a few more questions? Thank you very much for the talk. I wonder, my first impression is similar to him. So you talk about the noise, and to me, the noise is like a quantum related to the quantum, the randomness in the problem you want to solve. So that problem itself is not Bayesian, right? Because I saw that NFT is not Bayesian, and the PSR is also not Bayesian. And in order to apply the core, you first made the Bayesian version of those two algorithms. So I want to go back to the beginning of your talk. Why you want to consider the confidence region of the input variable, maybe not a random variable because it's Bayesian. I mean, no, you constrain on the prediction of confidence for the prediction function. You have the upper bound and the lower bound, and you use the Gaussian process view of point to handle it. But why? If the problem you want to solve itself is not a Bayesian in the beginning, why you don't consider the confidence interval of the output y?
Sorry, we consider, but
because no, you set some constraint on the output y, right? For example, in the first few, or maybe next slide. This one, because this is GP, so you have the prediction function as the blue, and the upper bound and lower bound with the required accuracy, and then you consider some confidence region. that's the region set on the input X. So in frequentist, we have point estimation to like for this input X, what should be the expected response Y, right? And we can have the confidence interval, some like this. I mean, why you don't look at this from the other direction?
I mean, basically, I mean, the previous acquisition functions basically
Because you want to
consider,
use them, so you have to use the Bayesian viewpoint.
Uh,
No need to-
I don't stick to Bayesian, but I mean, if we know uncertainty, it's better to use it, right?
Yeah, I mean, in active learning, people also use uncertainty to guess what should be, where should we collect the next X and try to label the Y. For example, in active regression, but people in active regression will view the uncertainty in another way. The uncertainty of the confidence interval of the Y given some fixed X. But here it's like the confidence region is defined for X.
Okay, so I think, I mean, this confidence confident region is not I mean,
Not for X.
it's for X.
Yeah, so my question is just why you want to focus on the confidence region on X rather than the confidence interval for Y?
Okay, so I actually don't know how we can cope with this situation
okay.
without this notion.
I see. Because if you, for this specific problem, if you use a very carefully chosen kernel, you can have a very nice property.
Yeah.
I see. Okay, thank you.
Thank you. May I comment myself? Where is it? This is not on X, this uncertainty, right? This is on Y, because it's on the observed energy that we get from the quantum computer. The axis in these cases would be the parameters of the quantum circuit. So now I'm quite confused, like why is it the confidence on the X?
No, he just say, I mean, we have uncertainty or confidence interval in Y-axis, and why we need to define something in the input region. And the answer is this one. And I mean, it's not, I mean, we don't have uncertainty in X-axis.
Okay. Thank you. Do we have any more questions? Yes.
For your presentation, you show us the benchmark Hamiltonian. Is there any other benchmark Hamiltonian?
So yes, okay. I don't know much, but I mean, people uses Hubbard model for benchmark, and also, I mean, sometimes people really want to compute. I mean, it's still benchmarking. Is that lithium? You know, I don't know.
Yeah, lithium. So this is Heisenberg, the Heisenberg Hamiltonian, just for the benchmark. And some colleagues of us, they also used like I think lithium polymer, something. I think they.
So the exact solution of the ground state of the Hubbard model is well known. Not yet.
I'm not sure about Hubbard model.
Yeah, I'm also not sure. I think like it comes to the dimensionality problem.
So can you estimate the difference between the approximation and the exact solution in this case?
Yes, in this case, we always, I mean, it's a very small system, and we can always compute the ground state energy, and also ground state wave function we can analytically compute. And in this evaluation, we use them.
Yeah. Thank you for your presentation.
My question is, if I consider the idea of the core idea. Can I apply extend it to a more general quantum machine learning from like the quantum kernels rather than the ground state of computation?
So far, what we found is, I mean, core is useful in when we have specific kernel,
Yes.
which is not like universal kernel. And okay, and I don't know much about quantum machine learning kernel,
Okay.
quantum kernel. So
Yeah.
my answer is I don't know. Sorry.
No. Yeah, thanks very much. It's very strong.
The quantum machine learning is not the bottleneck. Bottleneck is you need to find some situation where considering core is beneficial, like in that slide.
Yeah. Thank you.
Right, thank you. Any more questions? Maybe online? I think we can take one or two more. That's not the case. All right, then let's thank the speaker again.
Thank you.